Hey, John here. We're looking at the FPGA build code for Project Nouveau that's in this GitHub repo here. There'll be links below this video on YouTube in the description. Today I want to talk about the synchronization in this module that allows the CPU to talk to our VDP, the video display processor, such that the CPU runs at its clock speed in the phi clock domain, which you can see down here, and the VDP runs at the graphics pixel speed in this clock domain here. A big thanks to everybody that supports my channel, especially the VIP Patreons listed here. Thank you very much. All right, so what are we doing here to get these things synchronized? Let's look at this module pretty closely here. These are pretty straightforward, generic synchronization implementations that you can find anywhere on any site that talks about Verilog and talk about signal synchronizers. A 3-bit long shift register, which you can see right there. I got write sync, I got read sync, and there should be a another one for the. Oh, this is just the OR of the other two. We'll come back to that in a minute. We have a write synchronization and a read synchronization, and these are the signals that come out of the CPU. Okay, we're looking at they come from higher level Verilog code at the top level file we've seen before more than once on my channel when we talk about the IO rec and the read signal combined. Okay, when those are both low, this signal that comes in here, the read, will be true. All the stuff in these modules are all active high logic, positive logic. If they need to be negative, they're flipped over before they come in here. And if I'm outputting something that's active high that needs to be flipped over and go out negative, it gets flipped out somewhere else. That way I don't have to remember all this garbage or put little underscore ends everywhere to remember what's high and what's low. It's a huge pain in the butt. Once you're inside your internal logic, it doesn't matter. Make everything positive logic, make all the names mean a truthful word when it is set to true. So you don't have the enable interrupt where you set it to false in order to enable it, blah, 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 blah. You know, that is stupid. I don't want to do that. Okay. So the point is these are active low, but they're flipped over before they come in. And the read signal here comes from the higher level thing. It's active high. Not that one, doofus. The CPU read and CPU write come from the top.v file here, all the way down here at the bottom. It comes from this logic right here, and we've seen this multiple times, this style that I do in the top file. So this is true when both IO rec is low and read is low, which you can see up here where it's actually created. I don't know where it is. Here it is. Here we go. When IO rec is low and read is low, then that's true. And the same thing for writing. Okay, so there's your bearings. There's your context here. That's where that all comes from. Now, that's all fine and dandy, except for the fact that it comes in the CPU clock domain, and we need it in our pixel, our graphics clock domain. All right? So we have a pulse that goes true to represents this period when we're trying to do an IO operation from the CPU so we can access the VDP registers or the memory or whatnot. We have another signal that goes true when read is active and IO rec is true here. And additionally, as you just saw, those are also filtered and only become true when the CPU is actually trying to access the VDP. So these are already fully decoded from the CPU's perspective in the CPU's phi clock domain. When that's true, I will write to the VDP. When this is true, I will read from the VDP from the CPU's perspective, okay? Now we have to synchronize those to deal with the potential metastability issues that can arise as a result of when these signals change, right? Our decoded read and write signals here that come in and are used here and here. We need to make sure that those things don't change in an awkward time. Because if we run this test bench, now this has a test bench for it, so let's go ahead and I'll show you what I mean. You do this in order to bring that up. I'm going to run it in the background. And I think I showed this once before. It takes a little while to run this one, because what this particular test bench does, and this is because I was lazy and I created a file, and I mentioned this before, that needs refactoring, because this will instantiate submodules, and it also has its own processes and things in it, which is the ones that do the signal synchronization that we're just looking at. So in order to simulate this, I gotta simulate the whole universe, which is not always convenient, okay? It's just barely tolerable for this. So I'm gonna leave it go until it drives me nuts, and then I'll refactor it. So what we're looking at is this. The CPU will assert, here's our, well, there's a VDP mode tick. There we go. Here's the read and the write. These are the decoded ones from the top level module, all right? And we don't even pass the whole address in here. We only pass this mode bit, which is the least significant address from the CPU, because we only have 2 registers in the VDP. We only have 1 address bit that we care about. It'll be 1 if we're accessing port 81 from the CPU perspective, and this will be 0 when we're accessing port 80 from the CPU's perspective, all right? So what we're looking at, right now we don't care why the CPU and why this test bench is talking to these registers. We just care that it is, and we want to look and see at what's going on with the synchronizer here, this shift register, and the timing relationship in here to make sure that when we're all done, we have the data we need when we need it, okay? So here's the pixel clock. And that represents the edges on here represent when the VDP is ready to do things on these rising edges. More often than not, we do everything on these rising edges. The CPU is synchronized to the rising or falling edges of the V clock up here. So here's the problem. If we have this, write or a read signal, these decoded from the CPU, right? If this edge comes too close to one of these rising phi edges, we end up with a metastability problem. That is the definition of a metastability problem. With the context, I should include the fact that the rising edge of this pixel clock here is the one that triggers our various synchronous logic, okay? So in this particular case, we're fine, but let's zoom out a little bit here. Let's look at all these other times when the registers are being read and written. Where is this related to the rising edge of phi? That's real bad. So this may not be making the setup time here. It could. I mean, FPGAs are pretty fast, and this is the actual number of nanos. I set up the test bench with realistic time values in here. So if you zoom way in on this, and you lay down the white marker here, and you put this one there, it'll tell you this is what? 2 nanoseconds between here and there. What is the setup time for the FPGA inputs? 2 nanos is pretty close. Now, that could be a problem if you simply said, what's the value here, and I'm going to use it on this rising edge. It may not be stable here, okay? Now, in the simulation, what is it doing here? It did see that it's a 1, which is what's shifting in down here, and we'll take a closer look at why that is in a little bit. Okay, so but the simulation has an infinitesimally small setup and hold time. 2 nanos may not be good enough. Now let's look at the other edge over here. Oops, how about this one? He's looking pretty good. So what happens is in this particular test case, this is terrible. This particular test case, the phase, these things do slosh around a little bit. Again, we got 1 or 2 nanos on there. This one here looks okay. All right, so this is what our problem is. We're not meeting the setup and hold time relative to the pixel clock where the VDP logic is all going to run on. And that logic and the pixel clock is the thing that it's going to use to latch things in its register. So it gives us plenty of time here, which is kind of frustrating. But because our clock is chattering along it whenever it wants to, without respect to the CPU clock, the time we're looking at this can vary a little bit. So what we do is we're going to create a shift register. And we're going to say every time there's a rising edge here on phi, I'm going to take what I believe is, the latest, greatest. I'm going to just clock in and latch whatever's on this right register up here, and it may or may not be metastable. Odds are, even if it does wander around a little bit and it's metastable, it'll settle down by the time you get over here. This amount of time between these two is what? 40 nanoseconds. That's actually a long time. So if it wanders around and it settles to a 0 or a 1, we should be fine by the time we get over here. So we're building a shift register, and I'm wasting time re-explaining how synchronizers work, but the short of it is, this is what we're looking at in here today, a type of synchronization that is a really basic one, and we will see that we need 2 full pixel clock periods to react if we use the synchronizer that I've designed here. And you can see that it actually, what is it doing? Oh, we're going to see I did a little bit of sloppiness in here, and I'm going to grab the data even after the one period. But we need 2 whole periods before we're golden. It is in this second period here that we assert this tick signal here. That's actually for the mode. We'll look at that in a minute. Here's the right tick in the code that we were just looking at. Occurs here in this second period of this shifting in, okay? So this is where we do our synchronization. It is when this thing falls after the rising edge on this pix clock, on that edge right there is when the VDP will consume the data that the CPU is writing to it. And you can see the data up there is an 80 in hex on the data bus up here, okay? Now, provided that this happens, well, the CPU still has the data on the data bus, we're good, okay? So what is our worst scenario? In fact, the worst scenario, this is probably our best scenario at the moment, because the simulation sees on the rising edge right there that the right signal to the module is 1, which is why we see this happening there. We'll look more closely at that in a minute. So this is our best scenario. It went high, we saw it right away, and we're on our way. What about a worse scenario? A worse scenario would be when the pix clock here goes high just before this rises, and the VDP logic does not know yet that this has been risen until the very next time there's a rising edge on the pixel clock. Okay? That would be terrible, because then, and we can clearly see that would only be 2 or 3 nanoseconds off earlier than this, okay? Then what would happen is this edge here and the reaction of the VDP would be what's happening over here in the current scenario. And it wouldn't be until this edge here arrives that this, I keep pointing at the wrong one, the tick down here, or both of them for that matter, go true to tell the VDP to latch on in the next rising edge, which would be the one over here, and grab the data from the CPU. And you can clearly see the problem here. This 80 in the worst case timing scenario, which I had plotted up, all the times and stuff are based on the worst case scenario here. It could have removed the data from the data bus and I get garbage in the VDP when the CPU tried to write to it. That's a problem. Now, you can see in this timing diagram some mystery thing called VDP data in grabbed a copy of this 80 and it held onto it a long time. And if I zoom out, it holds onto it all the way until the very next time the CPU tries to write some data over to the VDP. So our goal today is to make sure that if we need to extend the value on the 80, like one of the pulse stretcher things I talked about before, that we have it in place, we need to also look at the situation and ask, what can happen? I mean, if you think about it, if Pix clock is running at, a whole lot faster than it really is, if it's running, 100 times faster than phi, then it would be going chugging along like crazy, and you would definitely notice that it went from 0 to a 1 real fast, because it would be going clock, 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 and by the time this thing shifted through to get to the point where there's this 110, it would happen very early on in here, and we wouldn't care at all. We just say, let her go, let her fly, we don't need to do anything special. But the reality is that the Pix clock frequency is not that much faster than phi. It's fast enough that what we do know is that we will have, what do we got here? I'll put a white marker there and bring it over. Here's one pixel clock period, right? Here's another pixel clock period, and a half. We know that, and this is the worst case scenario, so this is as short and narrow as it could ever be based on the Z80 timing specs. In reality, it's longer. I've looked at it on the scope. These are much longer and much more palatable on the chip that I have. However, if you run it and it gets too hot or it's too cold, or as the thing ages, this is going to be the worst case thing you're going to have to put up with. And it'd be nice to know that we can handle that. Worst case being, there won't be enough of these pixel clocks to advance our logic to recognize that what we need is to grab the data off the data bus and store it in one of the registers, okay? So what I've decided to do is, arbitrarily make the decision that it's actually okay, provided that when we grab this, we grab it a little earlier than we normally would. Normally what you do in a synchronizer is create your 3-bit shift register type of thing, and when the second 2 bits have received this pulse, so this whole thing about this metastable thing that could occur on the first bit in your shift register, what you see down here, it goes from 000 to 100 here, because it saw this go up. But if it doesn't do this and it wobbles around, it might be 100, or it might end up 000. It could quiver a while. And you really don't want to take advantage of the value of that bit until way over here, when it is more likely to have stabilized. Okay? So what I've done is, you've got a whole pixel clock period long to wait for the metastability to settle out. When the second rising edge of the pixel clock comes along, we say, that's when I'm going to grab a copy of whatever's on the data bus. Because I know that the data bus is stable by then. Because the timing guarantees, if it's writing, that the data will be valid before write ever is valid. So I don't have to worry about metastability when I'm bringing in the data from the CPU. So I can grab it a little earlier. However, and even grab garbage. I could false trigger this if I want to, provided that it's stable when the VDP write tick signal pulse falls after this rising edge right there. Okay? It's okay. It could be 22 over here. Who cares? As long as the value I want, which in this case is 80, is on here and stable at the falling edge of this thing here, I'm good. Now, it turns out if this goes as late as possible instead of as early as possible, as it is right now, it can happen way over here, like I said before, and the data could actually disappear. That's why I steal this, as we'll see on the rising edge of, what will be this write tick. Okay? So the key is, how do I generate a write tick that occurs before the rug gets pulled out of my feet with the data going away on the bus from the Z80 from the CPU, okay? Well, what do we know? We know that the pixel clock is always going to be faster than the phi clock. Now, if you overclock your Z8S180 to 50 megahertz, this will not work. I was working on a design where that could be done and it would stretch and all this stuff. It got really complicated, really nasty, and I just said, you know what? I don't support that. We're running at realistic VGA speeds. The slowest it can ever go is going to be 25 megahertz. Okay, done. It'll always be faster than phi, and if that's the case, there will always be at least 2 periods, if not 2.5 periods of phi clock times in here for this signal to be recognized and shift up and so on and all that other fun stuff, okay? So I decided I'm going to use a simple implementation using these shift registers the way we're looking at right there. Okay, so here's what happens. Every time there's a positive edge on the pixel clock, both the write synchronization and the read synchronization logic will kick in and shift the raw signal from the CPU into our shift register. And what that means, and then we're shifting it to the right, obviously. So what that means is when it first changes from a 0 to a 1, okay, which is right there, it being when the CPU changes its the decoded signal goes true, goes active. We wait for our first following pix clock edge. At that time, we then shift it into our shift register. So that's why the shift register is all 0, 0, because it's clocking in all these zeros. It's always 0. All these down here are always being clocked in, and it's 0 and 0 and 0, and then down here it collects and it gets the 1. All right, so we now have a 1, 0, 0. When we do this one, it is a 1, 1, 0 because it clocked in a second one, shifted it to the right. And what we'll do is we'll see in the logic in our code that we'll simply ask if there's a 1 and a 0 in the right 2 bits of our shift register. That's the one and only one time where we have had 2 stable reads of a 1 into our shift register. And during this window is when we want to assert our 1 tick pulse that says over here is when you want to consume the data. Okay? And because, like I said before, this can slide later, and it might be that the falling edge on this thing here is way over here, what we need to do is steal a copy of the data while the getting's good. Okay? So that's what this is trying to do in here. So for the writing and the reading, these are the shift registers. Here's the tick signal that are getting decoded by asking if the 2 write bits are a 1, 0. Perfect. There's a mode tick that you also see. This is a tick signal that goes true if either of these is true. It's just a simple OR. And then what do we got here? This is the thing that steals the data. I need to stretch the data in case we are out of sync enough where the data is gone by the time we want to consume it. So what I'm going to do is on a positive edge of my right tick signal, I'm going to use that as the clock and just say at that point, just steal whatever's on the data bus. Okay? Now this is what we call a gated clock. It's sort of a disguised gated clock, but normally, a lot of synchronous circuits they don't recommend you do this sort of thing because what they want you to do is always use the clock for your system as a whole. This is a unique, special case. It's part of my synchronization logic. I do it on this, I use the positive edge of my right tick to steal a copy of the data bus because if I don't, I'll miss it if this whole thing is shifted to the right a little bit. Because the whole point of stealing the copy early is because it could go away by the time over here when the next clock comes along, which would be the one we use if we didn't see this here, because that's a close call. It could have seen a 0 and saw the 1 here, and the whole thing would then take place over these 3, at which point I'm in trouble, okay? So I'm going to steal a copy of what's on the data bus here. Now, if this thing fires any earlier, actually it can't. This is as early as it can ever go, okay? So because this rising edge is right after that one. It could go as much as all the way over here in a latest scenario, and you can see that the data and everything is still value, and these are realistic times up here. So this is safe to do. It meets the setup and the hold time of the FPGA, and we can closely look and evaluate what would happen if this thing happened earlier or later. We can see it always fits, but we need to steal a copy just in case. All right, so that's what's going on with data that's coming into the VDP from the CPU, so we can consume it after the CPU is moved on. Right? That's what's going on here. Same thing, exactly the same thing happens for the mode. And the mode, remember, is the address. We need to remember whether they're talking to port 80 or 81 from the CPU. So you got to remember what the address was and what the data we want to store. And we need to steal it while the getting's good. Now, this one's a little bit different because if you think about it, your reading goes the other way. And if you're not ready, you need to assert a wait state to the CPU. You know what I just said there? We don't care if we're not ready so much up here, provided that we eventually consume the data before the CPU comes back and messes with us again. And by that I mean this thing that we're stealing a copy here. It's okay if the VDP doesn't take the data until over here because it's still good. As long as it takes the data before it gets replaced way over here, we have all this time for the VDP to react to this. And the CPU doesn't know or care if we wait. Okay? But if the CPU wants to read something, we better have it there before this goes away. Or the CPU never gets to see it at all. Okay? So let's zoom way out here. This is a lot of other junk, but for what we need, I know there's a read cycle way back here in the simulation here. We can take a closer look at what's happening there. You know, there's another shift register going on, and this time it's the read synchronizer. So we know the write's okay as long as we get the data in time. Now we need to make sure the read's going to be okay too. Now the CPU does us a little bit of a favor here. It does let us know earlier than it does when it lets us know about the writes. This little teeny earlier window here helps us. Okay? We will know about reading and get a longer time to react than we know about the writing. For the same reason, these are, asymmetric. They want to give us as long as possible to react and get our data ready. And the write cycle, the CPU wants to have as long as possible and get its data ready and out on the data bus, okay? So this simply turns it around the other way. And these, again, are realistic times based on the tables and stuff in the data sheet. So what are we doing in here? See, we have the CPU data out here, and then there's a register. This is one of those things where I got a reg variable and a wire that have the same value because of the way the Verilog works. I can't assign a value to a wire. So these two are going to be the same. And I can just go ahead and delete the redundant one there to clean up our picture. So what happens here is this is the CPU D out in the unit under test here. And this is the value that we want to give back to the CPU. And you can see it goes active at a really weird time. There's no rising edge here. It goes active. It goes stable. It becomes stable on the falling edge of the PIX clock during the read tick pulse. Okay? Now, I chose to do it here to give the CPU as much time as possible. In theory, I could hold off to here. We're still good. This does, if you look up the numbers, it does meet the setup time. But it's annoying to do it there. I can do it here. It will be ready there. This over here, the VDP D out value of 80, this is reading the status register in the VDP. And that 80, this 8-bit there, is the interrupt bit status. Okay, we know about that, but right now we don't care so much about the context other than the fact that we want to read a value. And the value is only valid during this, during the read tick window here, okay? And after this falling edge, it goes away. So the CPU has to take it from the VDP on this rising edge of the pixel clock. And again, we have a really close race condition here. So I may not meet the setup time. Oops, I didn't want to do that. There we go. I might not be meeting the setup time if I wait all over here, okay? Now, it's not this edge here that we care about in the CPU. It's the hold time after this signal here falls, all right? I'm pretty confident that we do, all right? But this is not a lot of time in nanos. What do we got in there? This is, well, it's 29 nanos. And it turns out, remember the data sheet for the Z80 S180, almost everything has like a 25 nanosecond delay and all this other junk. So this actually is kind of, could be close if it's one of those things that requires it within 25 nanos. So what I decided to do is move it over here and say, oops, or rather, I'm using the falling edge of the pixel clock in the pixel clock domain to steal the signal from the middle of this tick pulse rather than waiting over here. And when I say it's ready, we can do that anyway, because I know that the setup time when we read the registers that are implemented inside the FPGA will be stable by this time, because I know that the period of pix clock is many nanoseconds long, all right? I mean, it's this, oops, I keep doing that. It's this many nanoseconds long. It's a 40 nano for the whole thing. So this is 20 nanos in here. I know that the spec of the FPGA, it would be hard to buy an FPGA that cannot have the value of its latches ready and stable within 20 nano. That's a long time in FPGA land. So I know I'll be stable. I can steal it on the lower falling edge here, even though the rest of the VDP is all clocked on this rising edge here, okay? So within 20 nanos, I'm going to have the value ready. I'm going to play the game with an extra latch, like I did for the write, and I'm going to take it, and that's what the CPU D out is. I'm going to store it in a latch, and I'm going to hold it forever, because the CPU might not read it until after I've taken it away, which happens right there. Okay, so I'm stretching the data bus going in the other direction in this scenario. All right, so that should work. I used to have this on a positive edge, which causes it to happen later, but this gives me another 25 nanos. The comment is wrong. It's really another 20, because this is running in the pixel clock domain, not in the CPU domain. Okay, so that's what's going on with this pulse stretcher. Here's this assignment that says the data out wire equals the data out reg value, and the data out reg value grabs its value from VDP data out on this negative going edge. In another video, we'll look inside here, and we'll look at how the registers themselves work inside the VDP and see where this actually comes from, which is the data out from in here. And of course, the short of it is, I would argue it's obvious. It comes from either the video RAM when you're reading the video RAM, or it comes from the registers that are inside the VDP based on the mode and what you've done previous to the time you're reading from the VDP. And I say that because we know that when you're in mode 1, what you're doing is you're reading the status register, which is why there's a mode right there. The mode 1 is set to 1. I want to read the status register. There's only one status register. Bang, here you go. And inside the VDP 99 module, you'll see it outputting it as soon as the tick signal goes active, and it holds it until it comes back down. So that's where this comes from. That's why this is valid during that window there. Once this thing comes down, the logic you just saw says that on every one of these falling edges, I'm going to grab a copy of this if and when the read tick is true. Okay. Oops, I got to get that out of the way. There we go. And that's what's going on right here. Okay. So this is how the synchronization logic works when we talk to our CPU in Project Nouveau for this VDP. It will only work if the pixel clock runs a little bit faster than the CPU clock, and in all the modes that you can put VGA in, if we actually don't play any games, right? All these, the slowest clock is 25 megahertz. You got 30, 40, 50, 100, and then way up, 100, 200, and so on. No matter what, if you're going to go to a VGA monitor and you're running it at the pixel clock speed, and at some point we can talk about some games we can play, because in theory we can run this at half this speed if we want to, but you'd have all your pixels will be twice the size, which just so coincidentally happens to be the case with the VDP, because the pixels are huge. But that's not what I'm doing. I really am running this at 25 megahertz, which is a little bit faster than the phi clock from the CPU. So the timing diagrams that we're looking at here in the very simplistic synchronization logic is, in my opinion, valid to do. Okay? If you play any games in the relationship of those clocks change in the wrong way, where the CPU phi starts running, equal to or faster than the pixel clock, what the code is that I'm giving you here will not work. Okay? So this means only good for old 8-bit CPUs, which is exactly what we've got, and it's nice and simple to understand, even though it probably took me an hour to explain it. So, what else is new? All right, so tune in next time. We'll work our way down this the module hierarchy of how all these pieces work by looking at what's inside VDP 99. Thanks for watching. I'll see you then.